Today we're going to look at resistor networks, which are circuits that have more than one resistor in them. So quick reminder, we know that the voltage equals the current times the resistance. This is what we call Ohm's law, this right here. And we've worked with it for a while. And the thing we're going to say today is Ohm's law is true for every part of a circuit. So we can apply Ohm's law to the whole circuit, or we can apply it to just one part of the circuit. We are also going to need the fact that the power is equal to the current times the voltage. So this is the rate that energy is transferred. You guys know that. And then this was our circuit model. Remember, a battery or a voltage source acts like an escalator. It adds energy to the charges. In this picture, it's adding potential energy due to gravity. In an electrical circuit, it adds potential energy due to the electric field. But either way, it adds energy. The charges flow around the wires without losing any energy. They go through this thing we call a resistor or a load, and they lose their energy, and then they go back to the escalator and get more energy. And so that's kind of what's going on right here. So this load, this resistor, stands for anything that uses up the energy, whether that's your phone, computer, a flashlight, it doesn't matter. So what we're going to look at today is what happens when resistors are in series. And you guys played with this in the lab on Tuesday. But when they are in series, the word series means you got to do one thing after the other, right? So Harry Potter, the books are a series because you read book 1, then you read book 2, then you read book 3. Resistors are in series if the current goes through one and then the next and then another one maybe, and then finally back to the battery. So the resistors are one after the other, and that's why we call it a series circuit. So a series circuit looks like this. We still have a battery adding energy. The charges have energy, so they move through the wires, and then they go through one resistor, and they lose some of their energy, but not all of it. And then they flow through another resistor and lose the rest of their energy. And so they get all the way back here. They've lost all their energy. So this is an analogy of a series circuit. We have two resistors, and the current must go through one and then the other. Okay? Some things we can tell about a series circuit. First of all, the current, the flow through one, must be the same as the flow through the other. So the flows are identical, and you figured this out, I1 equals I2 when you were in lab. You noticed the currents were the same when you had two resistors in series. Okay, now, the energy, the voltage. So here, this adds some voltage. Let's say this adds 9 volts. That's 9 joules of energy per coulomb. So these guys have 9 volts. They might lose 7 volts here, but if they lose 7 volts in this resistor, then we know that they must now lose 2. Because if you add 9 volts, sooner or later they're going to have to lose 9 volts of energy to get back to where they started, right? So because this is a closed loop, whatever you gain, you got to lose. So the voltage drop, the energy lost in resistor 1, that's from like here to here, that's got to equal the voltage, that's got to add up to the voltage drop in 2, which is from here to here, and those have got to equal what you gained. So in a series circuit, the same current flows through the resistors, both resistors, and the sum of the energy that is lost in the two resistors, so that's this energy here plus this energy here, that sum of energies has got to add up to the energy that was gained at the battery, the voltage source. So we're going to write that like this. If we have a series of resistors, so here's a battery, the current flows through R1 and then R2. We are going to call I total the current that comes out of the battery. That's the current flowing in the total circuit. We are going to call I1 the current that goes through resistor 1, and we're going to call I2 the current that goes through resistor 2. And so we can say that the total current is equal to I1, which is equal to I2. So that's going to be true for series resistors. On the other hand, the voltages add up. So whatever voltage we start with here, if I figure out how much voltage I lose here, we're going to call that V1, and I figure out how much voltage I lose here, we call that V2, and I add the voltages that I lose in the resistors, that's this, the voltages that I lose in the resistors, that's got to equal the voltage that I gained for the whole circuit, the battery, okay? So that leads us to the idea that if you want to know what is the total resistance of the whole circuit, The total resistance of the whole circuit can be found by taking resistance 1 plus resistance 2. Okay, so this is in your toolbox, and that's also what you found in lab on Tuesday when we did the simulation with the resistors in series. So you know you have a series circuit when the current goes through one object and then the next and then the next. Okay, so think Christmas lights. If one of these bulbs burns out, if this little filament melts, then the entire circuit goes dark. The current stops flowing. So you have to have a complete circuit to make this work, and if any one part fails, then the entire circuit goes out. So that's like Christmas tree bulbs. So let's solve an example with this idea of series circuits. Okay, so here's the problem we're going to solve. I've got a voltage of 12 volts. It is causing charges to flow. The charges flow around the circuit. They lose some energy here. Then they flow to this resistor and they lose some energy, and then they get back to the battery. So what I know is that if I start with 12 volts of energy, sooner or later I've got to lose 12. Okay, and I also know the currents are the same. So I'm going to model for you how you solve these problems. So when you get them on your problem set, you are going to solve them, just sort of lay them out the way I am too, okay? So it's a little different than our usual solutions, but you've got to start by making a diagram. And now I'm going to think about three things. I'm going to think about the total circuit first, okay? So for the total circuit, here's what we know. We know the voltage is 12 volts. We also know that the total resistance would be R1 plus R2, which is 8 plus 24, or 32 ohms. Now, if we know the total voltage and the total resistance, we can use Ohm's law, V equals IR. We know the total voltage, and we know the total resistance, we can find the total current. So the total current will be the total voltage over the total resistance. So you can take 12 divided by 32, and you get 0.375 amps. So that is the total current that flows in the circuit. That's what flows out of the battery. We can also find the power, because power equals I times V. So if you know the total voltage and the total current, you can find the power is 4.5, and that would be watts. Now, once we know the current is 0.375 amps, then we know that current's going to be the same in each resistor. So we're going to look at each resistor individually. So for R1, that's this one right here, what we know is the resistance is 8 ohms. That's given in the problem. We also know that the current, I1, is the same as I total, which is 0.375. So if we know the resistance of 1 and we know the current in 1, we can find the voltage in 1 because we use Ohm's law, V equals IR. So this is what I mean by applying it to just part of the circuit. You can apply Ohm's law to resistor 1. So if you know I1, 0.375, and you know R1, which is 8, you can multiply them and you get 3 volts. You can also find the power. It's I1 times V1, which when you plug it in is 1.125 watts. All right, now let's look at R2. For R2, we know the resistance is 24 ohms. We know the current is 0.375 because the currents are the same everywhere in a series circuit. So we know the resistance and we know the current. We can find the voltage, and it's 9 volts. And we can find the power, and it's I2 times V2, which we have those in things, and we can find it's 3.375. And now we can check and see if our solution is correct. Because we said that if we gain 12 volts, sooner or later we got to lose 12 volts. Well, here in R2, we lose 9 volts, and in R1, we lose 3 volts. 3 plus 9 add up to 12, which is what we started with. You can also check the power. If resistor 1 loses 1 and 1/8 of a watt, and resistor 2 loses 3 and 3/8, you can add those together, and that's 4 and 4/8, or 4.5 watts. So the power should also add up. Okay? So that's how we solve a problem, and you can put these side by side, or you can put these sort of, the first couple lines solve R total. Just make sure you're telling me what you're doing. Like, see how I kind of made a little box here or something? So when you're using these equations, make sure it's clear what you're applying them to. Okay? All right. So that's kind of how a solution is going to look. Now, the other way we can arrange resistors is what's called parallel. And parallel means that As the current comes out of the battery, it splits up. Some of the current goes through one resistor, and some of the current goes through the other resistor. It doesn't all go through the same resistor, okay? Here is a gravitational analogy with the marble run for a parallel circuit. So you can imagine an escalator adding energy to the marbles. The marbles roll along the wire, and then at some point, there's a junction, a split. Some of the marbles go this way and down and do their work, and some of them go this way, and then they go down and do their work. The thing to notice is the current, the flow through this resistor, does not have to be the same as the flow through this resistor. And in fact, this resistor right here has more flow. It has a smaller resistance, so most of the charges take the path of least resistance, which is kind of where that analogy or that phrase comes from. What we can tell, though, is that however much energy you add, so this is the voltage of the battery, whatever that is, it's the same as the voltage for resistor 1, or the energy loss in resistor 1, which is the same as the energy loss for resistor 2. So the voltage loss in each resistor is the same. The drop, how much energy it goes down from here to here and from there to there, are the same in each resistor. And whatever current you have coming out of the battery has got to equal whatever goes this way, we'll call that I1, plus whatever goes this way, which we'll call I2. So I1 plus I2 have got to add up to I total. So here's how we will draw it schematically. We have a battery, current is coming out. This is the total current coming out of the battery. It will split up into I1 and I2. What we know is that V1 and V2 are the same. So the voltage V1 and V2 are the same for parallel resistors, and the currents add up. Now, as a result of this, the resistances don't add up. So what you guys found in lab was that there was a goofy way to add the resistances, and this is what it is. If you want to find the total resistance of two resistors or more in parallel, you add the reciprocals. So 1 over R1 plus 1 over R2 tells you 1 over the total resistance. Okay? So we're going to use that, and I'll show you an example of that in a minute. All right, so that should be in your toolbox too. So here's what we got. I've got a 12-volt battery. I still have an 8-ohm resistor and a 24-ohm resistor, but they are now in parallel. So to solve this problem, the first thing I got to do is find the total resistance. So the 1 over the total will be 1 over R1 plus 1 over R2. I can plug in my numbers. 1 over 8 plus 1 over 24. 1 over 8 is 3 24ths, so I have 3 24ths plus 1 24th, which is 4 24ths, which is 1/6. Now here's where you gotta be careful. The total resistance is not 1/6. This, what you find on the right-hand side, is 1 over the total. So now I gotta take 1 over the left side, take the reciprocal of the left side, that gives me the total, and the reciprocal of the right side will just be 6. So the total resistance turns out to be 6 ohms. So I want you to notice that the total resistance for these two is actually less than the smallest one, okay? Adding resistors, when you put more resistors in parallel, you allow more current to flow, which means there's less resistance that is encountered overall by the battery. Okay, now, quick note, when you solve this for R total, this is not R total, this is 1 over R total. To get R total by itself, you gotta take the reciprocal, or take 1 over the left side. So in order to find R total, you gotta take 1 over the right side. So don't write this down in your toolbox, because that's not the answer you can start with. But when you solve this equation for R total, it's gonna look like this. It's gonna be 1 over R1 plus 1 over R2. So that's how you're gonna find the total resistance when it's time to actually get the number, okay? All right, so now, the whole circuit. We now know the total resistance for the whole circuit. We know the voltage on the whole circuit is 12 volts. That's right here. We just found the total resistance, which was 6 ohms. And so now we can find the total current because we can use Ohm's law. The total current is the voltage divided by the resistance. So take your voltage, 12, divided by the resistance, 6, and you get 2 amps. So that is the total current flowing out of the battery. We can also find the total power. It's I times V, which is 2 times 12, and 24 watts is what you get, okay? Now, let's look at R1. So the current comes out here, and some of it goes through here. All right? So what do we know about R1? Well, we know the voltages are always the same for parallel circuits. So V1 is the same as V total, which is 12 volts. So now we know R1, and we know V1, we can find I1. I is V over R. That's 1.5 amps. We can also find the power. So P1, the power in resistor 1, is I times V, which would be 1.5 times 12, which is 18 watts. Okay? All right, now, if we look at R2, we know it's 24 ohms. So some of the current comes this way. Now, because this is 8 ohms, it's the path of least resistance. We would expect most of the current to go through this resistor and back, but some of it does go through here, but we would expect I2 to be less than I1 because it has a higher resistance. So we know the resistance, we know the voltages are all the same. We can find I2, it's V2 over R2, and we get 0.5 amps, which makes sense. It's less than 1.5. Less current went through the bigger resistor. We can also find the power, and then we can do a quick check. Does the current that goes through I2, or R2, plus the current that goes through I1, does that add up to the total current? And that's pretty easy to do for this one. 1.5 plus 0.5 adds up to 2. So we have 2 amps of current coming out of the battery, 1.5 amps goes this way, and 0.5 amps goes that way. And then when they rejoin, you're back to 2 amps going back to the battery. Okay? So this all holds together, it works. All right, so here's another analogy to just kind of show you what's going on. So this is a water analogy.
Strikes aside.
And
Electricity is
talking here on it. So what I'm going to show you here is what we have is a guy adding energy to water. So he's pumping it out of the lake and it's putting it up here. So this water has gravitational potential energy. It can then flow, and because of the gravitational potential energy it has, as it falls, it can do work. So this is an analogy of a battery with a single resistor. If I increase the voltage, what I am doing is basically raising the tower. So this has more potential energy due to gravity, so that's like charges with more voltage. And of course, if there's more voltage, there's more flow, and you can do more work here at the skill saw. Okay? Now, what would happen if I had a series resistor? Well, that would look like this. The guy is still pumping water. Water is being pumped up to the reservoir. A single stream of water is flowing down, and some of the energy is lost here, and some of the energy is lost here. Okay? So what we know here is that the current, the flow, is the same for both resistors. All right? But the voltages, how much energy they each get, might be different. But it'll definitely add up to what they start with. In parallel, it looks more like this. The voltage adds energy to the water, and now the water flows in 2 streams. Some of the water goes this way, loses all of its energy, and some of the water goes this way and loses all of its energy. And you have 2 things doing work, and this flow is not necessarily the same as that flow. They can be different. Okay? So that's sort of a gravitational analogy for resistors in series and parallel. So here's the big summary table. You can pause the video here if you want to jot any of this down. When we have series circuits, the resistance is the sum of the 2, the current is the same, and the voltages add up. When we have a parallel circuit, the resistances add as reciprocals. The currents add up, and the voltages are all the same. So feel free to pause the video and jot down that if you want. We're going to be using that. Okay? All right, so what would happen if we had 3 resistors? It's not that big of a deal. Don't panic. The total resistance would be R1 plus R2 plus R3. And the total current will still be the same as the current in resistor 1, which will equal I2, which will equal I3. And whatever voltage you gain due to the battery, that will add up to the voltages of each resistor. So if you lose 3 here and you lose 2 here, then you've got 4 left to lose there. Okay? So it's the exact same principle. All right, so that'll get you going on the problem set. So go ahead and find the problems, and you're going to work through them. Both examples that I solved are saved for you, and you just kind of need to show your work the way I did. All right? Okay, good luck.